Okay, so welcome everyone to Guided Study Group, week 10 of Math 141. So, it's not actually week 10, it's week 11, counting on your academic calendar. But anyway, so this is the exam 2 week. So there's not gonna be any new materials, even though I'm gonna go through a little bit of section 3.7 because I saw one of the questions in your practice exam is related to that one, and I think it's like extra credit lectures in class, so I think a lot of you might have skipped it. So I'm just gonna quickly go over this to give you kind of like an overview of what to expect and how to do the problems and all of that. And then I'm gonna have like a quick review of all the sections for this midterm too, as well as some practice problems I take either from previous practice exam or this practice exam, because again, as I said last week, I would highly recommend you guys do this practice exam before the actual exam. But then this time when I checked it last night, it's only 2 people did it. So I'm just going to base on that result, and then I wouldn't be able to cover as many questions and be as helpful as you expected it to be. So exam 2, first is section 2.9, which we're going to do with linear approximation and tangent line approximation. And also we have differential approximation. So linear approximation is basically one of the applications of derivative is when you use tangent line approximation. So to estimate a value of fb, with b is relatively close to a, but it's not a very nice value for you to just plug in and find the numbers. So the linearization say that it's L of x is going to equal f of a, which a is fa is easy to find, so just plug in, plus f prime of a multiply x minus a. So f prime of a is where you have the derivative of f prime of x and plug in a. And then you have differentials approximation, kind of like similar to the same, kind of like the same concept, but with just a different notations. Where you have delta y is equal to f of x plus delta y minus f of x. And so when you have f of a plus delta y, so that value of f of b can be represented as f of a plus dx. It's going to equal approximately fa plus dy, which we wrote it this way. So dy over dx is kind of the same thing of f prime of x, and then this one is kind of like delta x, kind of similar. So that differentials and linear approximation. Then you also have things starting in chapter 3 where you learn about critical number, which is defined as a number c in the domain of f such that f prime of c equal to 0 or does not exist. Extreme value theorem. So kind of like giving us an idea that if you have a continuous function on a closed interval, then it'll definitely have an absolute maximum and absolute minimum in that interval. And to find those two values, you use the closed interval method. The closed interval method to find the absolute max and min values of a continuous function on an interval is first step. This step is like find all critical number, and then find the value of f at critical number and the endpoints of that interval. And then the largest is going to be absolute max, and the smallest is going to be absolute min. So it's very basic, and you guys should be really familiar with these now. Then we have Rolle's theorem and mean value theorem. So for the purpose of remembering, as I said, just remember one of the things. So I would highly recommend remember mean value theorem and just notify that the Rolle's theorem is a special case of the mean value theorem. So both of them said that if you have a function that is continuous on a closed interval and differentiable on that interval, then the Rolle's theorem say if you have an additional condition of fa equal to fb, then there will exist at least a number c in this interval such that f prime of c is equal to 0. Or more generally, by the mean value theorem, it say they're gonna be existing number c such that f prime of c is equal to fb minus fa divided by b minus a, which indicates that if you have fa equal to fb, or the special case of the Rolle's theorem, this is gonna be 0. So, and this is gonna, I think that this is kind of like a very important concept, so make sure that you know that. Just in case in the exam you were given something related to f prime of c and you have no idea how it relates to fb, fa, and b and a. Here we have things more related to like the property of a function, how it increasing and decreasing, and the application of the first derivative. So we have increasing and decreasing tests, which allow us to conclude that on whatever intervals that f is increasing or decreasing based on the sign of f prime of x. So if f prime of x is positive on an interval, then f is increasing, and the other way around. First derivative test, which allow us most of the time to find the local max and local min. And I would say, even though we talk about local max and local mean in the second derivative test, most of the time you're just going to use the first derivative test because it's quicker, it's easy for your for kind of like visualization, instead of the second derivative test is more like, you know, computation and doing algebras and finding numbers. Those things is not really like, I would not really recommend it. You guys remember things better on graphs, so do it first derivative test. If you have c is the critical number of that function, continuous function f. If f prime change size from plus to minus when you go from left to right of c, then you have a maximum. And if you put it in the way, as I said, in the way of this thing, so you have c. If f change from plus to minus, so this thing can be 0 or does not exist, and you have a maximum here. Or if you have c and you go from negative to positive, this thing can be does not exist or 0. So this is a minimum. So when f prime change size from negative to positive, then you have a local minimum at c. If it doesn't change size at all, remember, there will be no local maximum and local minimum. So the fact that a number is a critical number of a continuous function doesn't guarantee the fact that you have local max and local min at that point. So next is concavity test and second derivative test. As I said, second derivative test is more computational to find exactly what you have for a point. Is it a local minimum or a local maximum using the first and the second derivative. So first is concavity test. If you have a second derivative positive or OX in an interval, then it's concave outward, and if it's negative, it's concave downward. So that's easy. Second derivative test allow us to confirm or check out if f at a number is local minimum or local maximum. So you have if f prime of c equal to 0 and f double prime of c is bigger than 0, then you have local minimum. And the other way around, if you have f prime of c equal to 0 and f double prime of c smaller than 0, then you have local maximum. Now again, these two is when you have a chance, if you have like relatively easy f double prime of c, then you should be able to like, you know, plug in these number and do confirmations. or you can use a table in the first derivative test that I just mentioned. That will be more helpful. But in the case where you have a second derivative test, it's so complicated, and the question doesn't really ask about concavity or inflection points. Try to avoid spending a lot of time on just one question trying to find a second derivative, and use the second derivative test to just confirm that is it a local max, local min. There are other ways that you can, rationalize in the questions, especially just based on the first derivative. Then you have section 3.5 is mostly checklists for curve sketching. The things that you need for just to sketch a curve is domain, intercept, symmetry. These are very basic, and you don't even need to take this class to know those stuff. Then you need asymptote, horizontal, vertical, and slant asymptote. Slant asymptote, please review section 3.4. Oh no, 3.4 and 3.5, horizontal asymptote as well. Interval of increasing and decreasing, use the first derivative. Local max and local minimum, you can use first or second derivative. I would say the first is more preferred. If you use the first, looking for points where you have f prime of x, change the signs. Then you need concavity and inflection points to see where you have kind of like these curving inward outward. Use the second derivative. Now with the slant asymptote, do a quick revision on long division. So, and then based on what we learned, kind of like we go over last week, we're gonna find the slant asymptote by just dividing the numerator by the denominator, and especially these cases is just applying for 1 degree difference in the two highest power of the numerator and denominator. Then you have section 3.7. So 3.7 I didn't actually go over, but this is like an extra credit thing, and I feel like it's kind of like the most challenging part in this entire section. Maybe that's why like this semester Casher kind of like put it into extra, because last semester was required, but a lot of people, I guess, kind of struggle a little bit. So the way we're going to approach section 3.7 is that two tasks, find a function and its extreme values. So it's kind of like similar to optimization problems, but this one is more, complex, and you have to actually identify what is the function. It's not just that they give you the function and they're like, okay, find what is the maximum and minimum. You have to, the important part of this thing mostly is just derive that function. And this sometimes can be really challenging to people. Step is read the problem, understand it clearly, draw a diagram. That always work. And I would say like most of the time, if I have no freaking idea of like what to do with the questions, I would always draw it out, figuring the quantity kind of related to something that I know, and it's always helpful. Then introduce notation and express what is given and what is asked. That's when you start to introduce the quantity that you know, not the relationship yet, but put in the quantity, say like height, base ratio, or like surface area or something like that. Next step is the most important one. If you were able to introduce the familiar notations into the problems, then you should also be able to find the relationship between these quantities. So usually it's just like things related the height with the base area or the base dimensions, or the volume and surface area, things like that. It wouldn't be super complicated as get to like super long formula or things that you haven't known before. It usually is something that you have learned before. Then you write the ask quantity as a function of one variable and find domains. So this is also a thing. When you find a relationship, say if you have volume, it usually is the function of, say, the base dimension and the height. So if you want to use like what we learned so far, like first or second derivative to find maximum and minimum, you have to have only one variable. So either it's a function of a or it's a function of h. And this is to write this one. Usually in the question, you're going to be given one additional hint where you can link A and H together. So kind of like this is the way where you come to eliminate one of the variable and put everything in just one variable. Now, after that, you're gonna have something, maybe like a function of H only. Then to find the maximum and minimum, you also need to find the domain. So the domain is really where you kind of like come to limit your range of evaluations. So say if you just have H like that and you don't have a boundaries for it, the values, the maximum value may always be positive infinity and the minimum can be negative infinity. So the boundary is what actually gives you the maximum and minimum based on what we also use the closed interval method to find what is the absolute max and absolute min in this interval. Then just, here close interval method. So it's a lot of old things. It's just these two steps is kind of like a new thing when you come to derive the equations, but we're going to come to that in one of these coming practice questions. So that's all I have for the review. Now we're going to go through the practice questions. So as I say, these are taken from maybe one of the previous exam or your practice exam, I don't know. So I would say, please, again, if you haven't started, please try at least a little bit or even like half of it before you come to these sessions. I don't want you guys to just listen to this and copy out the answer. That will be really bad for practice. So first one is, let's y equal fx be a differentiable function on that interval. Then use a linear approximation or differentials to estimate f of 0.01. To estimate f of 0.1. So to do this, we use a linear approximation function. You have f of x is equal to f of a plus f prime of a multiply x minus a. So a here is equal to 0, f of 0 is equal to 1, and f prime of 0 is equal to negative 8. Therefore, you have your linear approximation. It's equal to f is equal to 1 plus negative a, 0.1 minus 0, which is going to be 1 minus 0.8, which is 0.2. So this is very easy. Just kind of like remind you guys a little bit because it's been a while since we touched on these materials. Next one is that we have find the critical numbers of this function in the interval. Again, this is where you're going to solve for find the x value so that you have f prime of x equal to 0 or does not exist. This is the important part. So here you have domain of x is negative infinity to infinity, or just r in general, on real number. So you have f prime of x is 1/3 x squared minus 6x plus 5 to the negative 2/3 by 2x minus 6. So this one is where you have 2x minus 3 divided by 3 multiply cubic root of this square. Now, looking at this, and I would recommend keep it in this form rather than this form, because the one on the left, like this one, is the one where you have that one is not clear in the form that it's a rational function, so you might miss the solutions where you have the f prime of x does not exist. So you solve for that equal to 0, meaning you're gonna have x equal to 3, and the thing in the denominator, x squared minus 6x plus 5, is different than 0. And this one is satisfied, so it's x equal to 3. Now when you solve f prime of x does not exist, is when you have x squared minus 6x plus 5 is equal to 0, or when you have x equal to 1 or 5. So having said that, all of the critical number are 1, 3, and 5. Note the fact here that you have 1 and 5, but it's you take both of them because both of them in the domain. If you have a domain, say it is R excluding these 2 points, then you don't even need to account for them in the final critical numbers. But here we have a domain including everything, so you're going to take both of that point as well. So that's the critical number finding. Then we have this one. Given that function, then you find the absolute max value and absolute minimum value. So this is where you're going to use the closed interval method. So you have f x is equal 4 minus x squared over x squared plus 8. The domain is R because the denominator is always bigger than 0, so you don't need to care about where the denominator is 0 to find the discontinuous point. So you have f prime of x, and this step should be easy now. X squared plus a squared negative 2x multiply x squared plus a minus 4 minus x squared 2x. So this one is going to give us negative 16x negative ax over x squared plus a squared. So this is negative 24x x squared plus a squared. Now again, this one, the denominator is always divided because it's always a positive number. Then you only need to find for the critical number, you only need to find the points where you have f prime of x is equal to 0, or you have x equal to 0. Now to find maximum and minimum, absolute max and absolute min, you have to also check the points at the end points of the interval as well. So you have f of 0 first is 4 over 8, which is half. Then you have f of negative 1 is 4 minus 1 over 9, so it's 1/3. And then f of 2 is going to be 0. Therefore, our conclusion based on the closed interval method is absolute max at x equal to 0, f of 0 is half. Then you have absolute minimum at x equal to f of 2 equal to 0. So again, a very basic one compared to what we did in its section, then their practice questions. So again, if you have any struggles, and especially in this point, you shouldn't be struggling at all. So please review if you have any problems solving this. And if you need any of my personal help, please feel free to email me. Let me know before the exam. Do not do that on the exam day because I would not pick up or answer emails on the exam final days for you to take the exam. Practice questions. The next one is suppose that f prime of x is a differentiable function defined on this interval from 1 to 5 such that f1 equal to negative 2, and for any number x you have f prime of x is smaller than or equal to 2. What's the maximum possible value of f5? So this is a strange one, but I guess I went over this in one of the sections. This is where we talk about the mean values theorem. So based on the mean value theorem, we have f is continuous and differentiable on 1 and 5. Then you have there exists at least, so this denotion is there exists one value of c such in 1 and 5 such that you have f prime of c is equal to f5 minus f1 divided by 4. And we have that for any number in this thing is always smaller than or equal to 2. Therefore, when you plug in, you have f5 plus 2 over 4 is smaller than or equal to 2. So you have f5 plus 2 is smaller than or equal to 8, or you have f of 5 is smaller than or equal to 6. So we say the absolute value of f5 is equal to 6, the maximum value in this interval based on what was given. So this is a strange one, but as long as you know how to do the problem, you should be good. So this is what I have for this practice questions. So everything is just based on the means value theorem. So make sure that you know what is means and Rolle's theorem and how to apply them. This is one of the way to apply them. Next one, find an equation for the slant asymptote. So this is where you actually come to section 3.5. And here, when you look at the rational function, the numerator, the highest power in the numerator is 1 power greater than the denominator. So this exercise also a mean that I try to make you guys review long division. So you have now, because the numerator have highest power bigger than highest power of denominator, we're going to use long division. So we have 3x cubed minus x squared plus 0x minus 2. I will say plus 0x. Just to make sure the fact that I keep the x there to see it. 3x. So we're just going to do the long division. Have 3x cubed divided by this. Multiply back 9x squared. When you go from here, change the sign. Make not minus 9x, so you hit plus 9x. So you're going to have negative 10x squared plus 9x minus 2. So what you're going to have is that negative 10 plus 10x squared, negative 30x plus 30x plus 30, change to here negative 30. So you have 39x minus 32. So we have this one is equal to 3x minus 10 plus 39x minus 32 divided by x squared plus 3x minus 3. So you have limit of x approaching infinity of fx minus 3x minus 10. This is limit of x approaching infinity of 39x minus 32 divided by x squared plus 3x minus 3. And since you look at here, the highest degree in the numerator is 1, while that value for the denominator is 2. Highest power in the denominator is 2. So the denominator as x approaching infinity is always going faster to infinity compared to the denominator. So this is where we have a small number divided by a very big number, which is going to be 0. Therefore, based on the definition of a slant asymptote, I concluded that y equal to 3x minus 10 is a slant asymptote. So that's all I have. You can check back by finding the limit of x approaching negative infinity of fx minus 3x minus 10 as well. And you're going to find that this one is also equal to 0. And again, it's the slant asymptote by our definition. Now, the next practice problems. For the function fx whose derivative is graphed below, what can we conclude about fx? Now, note that this is the derivative graphed. So don't just look at this and I'm like, okay, there's a maximum at here and a minimum there and the maximum here. That's not right. This is the graph of the derivative. So be very careful with using kind of like analyzing any problem. So you have so the first derivative can give us hint about local maximum, local maximum, local minimum, and where you have critical numbers and decreasing and increasing. So we're gonna explore all of that. So here, when you look at that, you have the special point of critical numbers. So you're gonna have critical number at x equal 0, 1, I think maybe 5.5 and 6. Then you have the derivative going from negative to negative again, and then positive here. So when you have x, f prime, and f, so you have 0, maybe 0, 1, 5.5, and then 6. So you have 0, 0, 0, 0. So let's look at the sign. You have negative, positive, negative, positive, and then negative again. So your actual function is going to go down, up, down, up, down. So at this point where you have maximum at here and here, x equal 1 and x equals 6. Then you have minimum at here and here. You have x equals 0 and 5.5. Of course, based on this, you can also say something about the signs of the second derivative of f. So looking at here, the function is increasing on this part and decreasing on that part, increasing and decreasing. So you can conclude about concavity as well. So concave upward is when you have the function of fx increasing. So you're gonna have from maybe negative infinity to half. Then you have increasing again from, I think this is 3 to 5.5. No, 5.75. So it's from 3 to 5.75. And then you have decreasing from half to 3. And then you have decreasing from 5.75 to positive infinity. So you can also conclude that concave upward and concave downward. Then you also have inflection point. When you have f double prime of x change the size, or when you have the graph of f prime of x, first derivative, go from increasing to decreasing. So inflection point at x equal half, and so you go from positive to negative. So from concave upward to concave downward. At 3, when you have concave downward to concave upward, and then at 5.75, when you have it goes from concave upward to concave downward. So that's all we have. Again, if you have any questions with this, I would highly recommend review, I think, section 3.5 or 3.3. But this is very important one to understand the graph and be able to draw conclusions about the properties of the function from the graph of its maybe derivative, or the graph of itself, or even the graph of the second derivative. So now next one is the last questions I have, which is the only one that relates to section 3.7. So I'm going to quickly go over this one, just like one of the question. So the step, as I say, for 3.7 is you read the problems, try to derive the diagrams, and then assign quantities and find the relationship between those quantities. So we have a water tank that have a shape of a point down circular cone. So circular cone with the base radius 4 meter and height 6 meter. So this one is So this one is 4 meter and height is 6 meter. If water is being pumped to the tank at a rate of 16 meter cube per minute, find rate of which the water level is rising when the water. So find the rate of change of water level. So water level, if we denote is at h, and you're gonna find dh over dt when h is equal to 3 meter. Now, why is it dH over dt and not something else? Because this is the change of water level with time. Here you have the change of volume with time. So everything we only have two dimensions, the length dimension and the time. So it had to change with time. And now how do we find this? So we have, since we already assigned the height to be h, so we can also assign like the radius of the water level at any moment is also r. So we have by all we know about circular cone, we have volume is going to be 1/3 pi r square of h. So with that, you're gonna have the relationship. Now the next step is try to put everything in just one variable. So let's look at the problem and see what else we haven't used. We have what's given us is dv over dt is 16 meter cube over for 1 minute, and we also have the radius and the height we haven't used. Here, that is where we have the relations. So since you pump in water, it's always gonna the shape of water take the shape of the container, so it's always gonna be water is always gonna be in the shape of the point down circular cone. So your radius and your height is going to have the same shape and the same ratio as what it is for the big container. For the actual big cone container, it's not going to change the shape. Like say you have a cone like this, and then your water is going to be like diagonal. This is not happening in reality, because this is a liquid. It takes the shape of the container. Therefore, you have the ratio of the radius and the height is equal to the ratio of the radius and the height of the container. So it's 4/6 or 2/3. Now when you put it back in, you're gonna have it's everything in just height. So you have 1/3 pi. So you have here r is equal to 2/3 h. So you have 4/9 x squared multiply h. Or if you just simplify this, you have 4 pi over 27 h cubed. Now the next step is you're gonna take derivative on both sides, because what we want to get is dH over dt, and we have used dV over dt as well. So we have dV over dt, take derivative on both sides with respect to time. You're gonna have 4 pi 20 over 27 is a constant, so you keep it. H cubed, when you take derivative, is 3x squared multiply dH over dt. Note here you cannot cancel out dH over dt simply because your water level is changing with time. So it's the change of water with time is not a constant number, because your water level is changing, and at every single water level the rate of change is going to be different. So this is a function of time. So you cannot just simplify, say, hey, this is equal to 1. You cannot do that, and especially here, this is what we're looking for. So now we have everything that we need. We have dV over dt. You have h squared when you give it h is equal to 3. So you can easily find what is dH over dt. So when you plug in everything, you're gonna have dH over dt is 4 over pi meters per minute. And say here, especially when you find it, you can see the fact that dH over dt is not 1. So you cannot just simplify it, right? So that is all we did for section 3.7. Again, the step is always draw a diagram. It always helps for me, at least. And then you assign the maybe familiar quantities like base, radius, and all of that. Then you find the relationship between all of those quantities. Final step is to base on whatever the questions give you. Try to put put the functions, the relationship that you just get in just one variable so that you can solve it. And it's usually helpful when you put it in the variable that you're looking for. Say here you have dh, you want to find dh over dt. It's more beneficial for you to put it in the form in the variable of h instead of r. Now, having said that, that's everything I have for today. If you want more practice questions, especially for this last problem, which we didn't really go over much in class, do this problem in the book. But I mean, since Dr. Catazina already said that this is optional or extra credit in the lectures, so I don't think this is that important as other part of your materials. So please review those stuff first. Do your practice exam. Do not rely on these answers. This is not helpful for your preparation for the exam. And let me know how it goes if you ever need help with anything. Just not on the exam time, because exam meeting is not going to allow me to answer your call or anything like that. So having said that, just gonna end the meeting here, and I'll see you guys next week. Good luck on the exam.